So I think it's 10:15, so let's go to time. Uh,
Get some questions for us.
It's Francisco's last lecture.
Awesome. So, thank you very much. Yeah, so today, the title of my lecture is going to be very different from what I spoke before, but I wanted to start by kind of like addressing something that I think Hossein mentioned that I didn't comment so much. And I think the point of this should be kind of like teach you also some of the scope of the previous results. One thing that I discussed was a lot of how things stabilize and how they can be delivered. Also, that I showed about the dynamics of these quantities. And I kind of didn't go into detail of exactly how those computations were made. So I wanted to kind of like just take 5 minutes at the start of today's lecture, kind of get into a little bit of the landscape of these numerical methods and maybe give you some references so that you can kind of like play with those things. So in general, there's kind of like this dichotomy, kind of like quantum mechanical simulations, where you have a trade-off between the system sizes that you can consider, in the sense of time, duration of the clock. So if you have systems that are kind of small, usually 20 spin on half is usually a good number to back to your mind. You have approaches that basically use that exact idealization and law methods that basically take the entire information of the wave function and are able to perform computation. And the idea there is that the reason why you have this factor of about 20 is that you need for every kind of like state for every state of your quantum system, you need to hold on to a particular complex number, this C factor. And then you can kind of see that the complexity of this fundamentally grows with the exponentially systems. And so you always have like a sharp wall on this value on which you can do the turn. A different approach, and this is kind of like already mentioned by Christian, is that you can use kind of these ansatz, for example, these major product states, where you use the structure of the wave function and kind of define your state in terms of the product of these tensors. You now have that you have in some sense a more efficient way of writing down. It's kind of like a parameter, which is this bond dimension. And as long as you set this bond dimension to be some number, you can do calculation for arbitrary system sizes. But because this encodes the entanglement of your system, you're often limited to some time scale that depends on the coupling circuit. The simple intuition is that the entanglement should grow linearly in time. The bond dimension, the bond dimension scales exponentially with the so you kind of like for even very large bond dimension, you're also limited kind of like a start. And finally, at the end, I actually discussed something very different because the transport on a system near infinite temperature, which actually falls a little bit outside of this place diagram. It's kind of like you can think of adding a third axis on this, which is kind of like the mixedness of the state. And there you can actually use tools that kind of take this MPS run state approaches and build them up into matrix product operators. And the tool that I'll just like briefly mention is this density matrix truncation that allows you to perform computation on these kinds of operators. It allows you to look at the dynamics and look at the dynamics in these models. So I just want to kind of like flesh in and kind of like highlight these kind of different perspectives and a little bit the habits before jumping into the rest of my talk. And so with that in mind, I'm going to stop here for 30 seconds and see if there's questions, either about this or anything that I talked about these lectures.
So RPS is something like mean field approximation where we have kind of some correlations. Or
you can think of that. I wouldn't think of it as a mean field because you're not necessarily doing the classical correlations. You're still maintaining a lot of entanglement, but you're kind of like limited by the amount of entanglement that you can pull. And you're kind of like chopping up when you do these procedures, chopping up all additional entanglement beyond what you can capture instead of bond dimension. You can sometimes make kind of mappings to kind of more classical motion and get that. But I don't, yeah. Does that kind of give you a figure? So,
Okay, yeah, I'm just wondering if I'm doing a PS with a fixed combination, what is the point of increasing my system between large?
yeah, so that's a good question. And often, usually it tells you that you might miss some dynamics. The question ends up being what are you capturing and what are you losing when you do the truncation? So maybe a point that you're raising is like, if I have some big size now to some finite line, the weekend is going to model to a particular block. So what kind of like behavior like it? So that's one of the reasons why NPS are not necessarily used so much for dynamics, is that you always have this kind of like effective length scale that's set by your bond dimension. That's kind of a struggle that people find. They're very useful for finding ground states, and that's kind of like this entire DMRG business. Because there you can you have usual precise statements about like how you're expecting that. Usually the ground state of one-dimensional systems are when they are gapped, they have like finite correlation length, and that tells you that you should also be able to describe it well with finite population. Then like the phenomenon, this is what Christian showed us with kind of like this having that a lot more structure.
Yeah, so do you need to assume some symmetry on the state of product state in useful? Or it's just allowed to assume that that would.
You have to assume that entanglement is not going to be that large. In general, you can assume symmetry properties, and then these become numerically much more efficient, but not necessarily for this particular. Okay.
For one like on the ballpark of features. So our state vectors are essentially random. Where like we need to make them approximately random for a kind of like completely asymmetric approach. Do we always need to take the most general form of matrix products?
So in this case, you're actually not involving states by themselves and then summing them together. You can solve the entire density operator. You don't need to kind of make that separation. The key insight for here is that if you take a pure state, you can basically take two columns of this, so you know that you have a good representation, you have a good MPS representation. But you also know that the identity, the fully mixed state, also has a symbol representation, where these are basically identity. So the goal of these kinds of approaches is that we know that the thermal state and the initial state are easy to represent. We just need to get over that kind of complexity of where correlation, coherences matter, protective dynamics. In principle, you might be able to get around by increasing or not the boundary.
Are these methods also valid for
So this is not because you assume that you have a clear state. You can do try to these like quantum trajectories. That's one way of doing open systems. This in principle is, and you can like blocking dynamics. I'm not sure if anyone has implemented that, but that's something we're thinking about.
Yes, you can make this a open system. You can also use MPS approaches, but therefore you have to kind of purify the state. Similar thing that you can do it like for pure states, you can just calculate them flying as matrix. But there you have to like purify, like vectorize your that state. It's actually doable here, but it's much more complicated. There when you process that, so they're pretty complicated.
I think like the way that you purify is kind of like an open problem, exactly how you should do it, what happened. So you can do it. I remember the on that. I'm not sure how much that depends on. Yeah. this is kind of like just to kind of like advertise this. So the idea here is that you can actually can do the truncation a little bit more physically motivated way. And that allows you to see the dynamics of the density measures better. So that's kind of like why pushing for this perspective rather than unification. Any other questions before we jump into topic of today's talk? Awesome. Okay, so I spent 2 lectures telling you about normalization in isolated quantum systems. And today I want to change gears and tell you a completely different story that builds a little bit on the stuff that Noreen told you. And I'll kind of like try to summarize these lectures on 2 slides, which is it's the advantage of standing on the shoulders of giants. And this is kind of like a quite recent result. It would be interesting to tell you how quantum sensing is in fact can display different forms of improvements. It's kind of like an interesting field that I find it very exciting, so I want to share that example with you all. And also comment that my collaborators, in particular Richard Battle, with whom we kind of drove this progress, but also Robert Wang, Chuang, and Sunon, who were Robert is now at Google/Caltech, and I am Sunon at MIT. And Richard is a grad student at MIT now in the UK. Awesome. So I want to kind of like just briefly review the things that Norman told you and kind of in a slightly different language that hopefully complements the way that he presented. And in a much faster way. So hopefully this is intelligent and also give you an opportunity to ask questions if something is unclear. And so the question in quantum sensing that Norman posed was there's this relationship between the way that we have quantum mechanics and like the characteristics of quantum mechanics and our ability to sense the physical world. And I'll use the same example as he does, which is what happens when you use a single qubit to try to measure magnitude. And kind of know what the process is that we should go do to kind of like achieve this. In some sense, you want to initialize your system in the plus state, and then time evolve your system under this Hamiltonian. And that gives you a little bit of an angle rotation. It's proportional to both the strength of your field, and also the experimental time that you allow yourself to conduct this experiment. And then at the end, you want to fundamentally try to back out data. Well, not an observable. What you do is in this case, you measure, for example, y, sigma y. And in principle, if you know exactly the magnitude of the sigma y expectation value, you can back out the angle that you process. And that gives you a very good measure of it. But we have this problem of quantum. When we do this experiment, we don't get 0.25, we can get +1 or -1. So we fundamentally need to average over many experiments to be able to distinguish whether I have exactly 50-50 chance of +1 or -1, and my average sigma y is 0.5, or if I actually have a tiny box. We can kind of like connect to this Federal bound idea that kind of that Norm presented, and kind of think of this problem as kind of distinguishability idea. So we have imagine I'm trying to measure a very small field, and fundamentally I'm trying to distinguish the distribution where the measurement outcomes are completely uniform, that's kind of like the slash line, or try to see a little bit of an imbalance that is caused by the fact that I have a little bit of data. And fundamentally, because I'm doing these experiments, I'm always having uncertainty on this experiment, on my ability to estimate this probability distribution. And to say that I'm able to measure a particular parameter fundamentally tells me that my uncertainty has to be smaller. So it turns out that by the classical averaging, we expected that the error in the uncertainty that we have in this parameter always goes as 1/square. For experiments, this is kind of like this classical central limit theorem, whereas strength over sigma, as I alluded to, is kind of like proportional to field times the experimental time. If we put all these together, think of these experiments, the number of experiments is the number of tests that I have combined with the total experiment time that I yet, we fundamentally reach the standard quantum limit that Norm already introduced. And this tells us that there is a fundamental limit to how small the field line I can measure, scaling wise, if I have a certain number of sensors, particular amount, integration time, each experiment is some time. So this hopefully is a review, but kind of like gives a some sense a quick and dirty way of explaining this the origin of this skill. So a different way of understanding that picks up on what Norm says is we can also analyze this experiment not one quantum sensor at a time, actually the dynamics of any. And then we know that the state we should prepare is this coherent state of all the spins, they're independent. And we can look at the enlarged block sphere, where now you can imagine that the height of this block sphere is proportional to n. Because I have this quantum shot noise, the representation of this coherent state has some width that is proportional to square root of it. And now I still have the same problem that I want to detect after some experimental time the difference in this angle. But the difference in this angle is kind of like how much the coherent state processes, which is the length divided by the size of the spin, which gives us this particular scaling. And the thing is again has a similar behavior. And again, we can plug this in and get exactly the same standard quantum limit. And it's kind of like any body way of seeing how the origin of this standard quantum limit comes, even if we have multiple. Yeah. And we can now try to back out the existence of this Heisenberg principle, this Heisenberg limit, by understanding exactly how much you can kind of like shift and deform this uncertainty principle law. This is not precisely right, but you can get a feeling that if this block sphere has kind of like size n, the most I can squeeze this to make sure that the total area is conserved is going to be I put all my uncertainty in the vertical direction, I squeeze the horizontal direction up to something of order 1. So this is not precisely correct. You need to think of the negativity of this distribution, but this kind of gives us an intuition that by using entangled states, kind of like manipulating the quantum correlations, we can manipulate the distribution of this much akin to the spin squeezing story that Norm told us. And in this case, what changes is that this error in my angle no longer has this vector square. The 1, whereas the amount of signal that I collect is still the same. So so even if you just visually you can understand, you're able to like distinguish the probability distribution that the end state for much smaller values of n. And that gives us kind of like this limit, which is the Heisenberg limit, the fundamental limit to our ability of detecting a signal. And for the duration of the talk, I'll mostly focus on kind of like scaling statements. And once everything's going to be up to the one that depends exactly on the details of the measurement and protocol itself. So let's start with that if not super clear. Okay. So this tells us again that one way of understanding is that quantum sensing appears to give us some limitations if we have an entangled particle. It also tells us that by manipulating our quantum systems in a precise way, we can actually improve things and do better than what we would naively expect. But one thing that I want to emphasize is that in the estimating a particular magnetic field, that's bad, as good. There's no additional resources that you can add to your experiment that allows you to curb this limitation. Because this is something that fundamentally just tells you, you have a state, you do a small perturbation, how well can you distinguish from a state that was not perturbed? And that there's no additional resource that allow you to do that. And the motivation for what I want to tell you now is, can we go beyond this? And can we think of settings where we can use different forms of quantum improvement to sense better the outside world? And the intuition and kind of like the pictorial thing that I want to emphasize is that a lot of these experiments and a lot of the ways that we often think of quantum sensing is in the context of a classical computer effectively controlling the quantum sensor. What we want to think is settings where quantum computer that is able to coherently manipulate and control this quantum sensor is able to give us some form of attack. And the problem that the setting that we'll try to think of is, well, the problem we want to tackle is this idea of broadband AC sensor. I told you that in terms of estimating fields and estimating parameters, we can do better. So we need to think of a different problem. And a very useful problem to think is this idea of trying to detect signals. So no longer trying to estimate the value of a parameter. It's more of a yes or no question. Is there a signal? And more specifically, I'm trying to look for oscillating fields of the form B cosine of omega t plus 5, where I don't know precisely the value of B, I don't know the value of the frequency, and I don't know the phase. I'm trying to guarantee, I'm trying to see if there's a signal within a particular frequency range that I'll denote as delta omega, and whose strength B is larger than some threshold. Okay? And this is a very natural problem because if you think of in successive particle physics, this is a lot of what they do. They have these exclusion plots where they look at the mass frequencies of the signal, and they have a coupling strength, which effectively is the strength of the signal that you're trying to measure. And they fundamentally want to try to, as quickly as possible, try to exclude or find whether or not there is such a signal in this branch. There's also more, in some sense, more down to earth application of this. If we think, for example, of NMR, you basically try to detect the presence of particular lower frequencies to understand the structure and the geometry of proteins. Instead of molecules. And that gives you a sense of like how the detection and the understanding of these kinds of problems is meaningful. And why is this problem particularly amenable to having some form of enhancement in this particular setting? The key is that you can think of this problem as a combination of two problems. One is that you have to sense the signal. Fundamentally, you have some outside signal, and you have to make sure that you're able to detect very small value of the signal strength, because you want this B to be as small as possible. You also have a notion, and this is where you have this kind of Heisenberg already. But on the other hand, there's kind of an interesting problem that you need to know where to look for it. There's kind of a notion on which you need to search for your signal across this frequency, this broadband frequency range. And that's, we know that there's a different kind of quantum advantage that often comes in the notion of the Grover algorithm for such a problem. So this kind of the goal of this and why we're interested in studying this problem is that it appears that there's a world where we can like leverage in some sense orthogonal advantages that quantum mechanics can give us to find a better way of saying. Is the motivation the same, the problem, and why we think we can solve it? Okay. So I'm going to kind of summarize over here the results and kind of like give you a little bit of an outline of what I want to start. So it turns out that if you want to solve this problem, if you do it classically, you have a fundamental limit to how fast you can. And that fundamental limit, I'll write it this way, you can understand as the total time that it takes to solve this problem is going to depend on how small your signal is, but also how many times you need to search for it. And the smaller the signal is, the more times you need to search for it on this method. Okay? And if you think of it, that tells you that if you have a particular, you can think of that part, if you have a finite time, for example, PhD, to look for axions in the universe, there's a particular amount of phase space of like this coupling strength and this frequency band that you can target. And that's what you use as convenience. If you have this form of quantum control, it turns out that the time it takes improves in a scalable way. In fact, this kind of like the second factor that you gets in quadratic. This means is that if you have a fixed amount of time, again, your PhD, you're fundamentally able to explore a much broader landscape. You're able to sense a much larger regime of signals. Okay. And what I want to do today is I want to kind of build an algorithm and tell you exactly how you can get it. You can do this. I want to kind of like show you or kind of allude to you that it's actually optimal. We actually have limitations, much like the Heisenberg limit has a limit on how well we can sense. There's a limitation to how fast we can solve this problem. And our algorithm matches those up to polylogarithmic factors. And finally, I want to kind of argue that when you hear quantum algorithm, always a little bit scary because you never know exactly how much control you have. But hopefully I'll try to convince you that the ingredients and the key ideas are quite simple. And this hopefully, what we think is kind of very interesting about this is that hopefully it can be realized and kind of used in your terms. And if nothing else, what I want to convince you is in some sense, quantum computation. We just need to understand the setting and the sensing setting on which we can leverage this quantum computation. I'm stop here a little bit for questions. If that was happy. Seems like so. Okay. So let's go back to the problem. The key insight I alluded to is that this rapid-based sensing is a combination of sensing and search. And I kind of already told you exactly how this sensing improvement comes to be from the use of correlated quantum mechanical correlated states of our sense. And so what I want to kind of give you, and just, hopefully this is a review, but if not, hopefully it'll be interesting. I'm going to tell you exactly how quantum mechanics gives us this Grover improvement, and then I'll tell you how we can plug it back into a sensing program. So to understand why quantum mechanics can do the search problem faster, it's important to kind of like review how we should think of classical search. So I'm going to define this kind of like very simply. Imagine that you have a drawer. You're trying to find a missing item, usually a pair of socks or your passport. If you are a classical being, which hopefully you are, the way that you solve this is you have to go effectively draw by the finger and check for whether or not you're there. Until effectively you reach the drawer that is the item. The reason why this is so frustrating every time we do it is that the time it takes you to find this always scales with the number of drawers that you. Effectively, if there's no prior distribution of where the path should be, you fundamentally have the problem gets worse. And the more messy you are, the more drawers you have in life. And fundamentally, this is a fundamental limit that says how well we can search over unstructured data. That's usually the way that this is. It turns out that if you have a quantum mechanics, you can do better. It's kind of like Grover's algorithm. And before going that, we should actually describe what we mean by looking for things on a drawer in a quantum mechanical way. And usually the way that this is framed is in terms of an object which is known as the origin. So the idea is that we have a quantum computer that has a number of vectors that the size of our search space. In this case, we have n drawers, so we'll have quantum computer with n existence. And what we mean when we check whether or not the item is there is that we can perform an operation in a quantum coherent fashion that basically applies marking operation if I found that if my element is in that particular drawer, which I'll denote by this. Okay. And what you should think is that whenever you check whether the item is there, is that you take your quantum state of your quantum computer, you throw it into your cupboard, and the return is that you have this oracle applied to your state. Okay? And this feels kind of like it feels natural. That is the simplest thing that we can use to identify whether the object is there. But hopefully demonstrate you very quickly how you can use it to build a better searching algorithm. Okay, and the solution is actually quite simple. So let me run through it. So the idea is that you initialize an equal superposition over the entire register set of your computer. And then you do it. You first send your state to your cover, apply this oracle operation, and then you do a different rotation called this diffusion operation. So this oracle, as I alluded to, just puts a minus sign on the marked element, on the k-star part of the wave function. And this diffusion effectively performs a rotation around the initial state that you compare the initial. So this is very intuitive why this works, but there's actually a super nice geometric description that I want to take. So what are we doing when we do these operations? So there's kind of two states that we care about. There's the state K star that tells me that kind of tell is where my item is going to be. And there's this S state that equals superposition. Now, usually this S state has to have a little bit of overlap with my end result because I compare the equal superposition, right? But when I run this order to the future, what I effectively do is I put a minus sign on the part of the wave function that has an overlap. So in this landscape, what it corresponds to is that it does a reflection around the x-axis of this kind of like two-dimensional. Okay. Now we can see what happens when we do this diffusion operator. I just do a reflection around this initial state. And if you look at it for more than 5 minutes, you can tell that the angle, if you start with some angles theta between your state and the x-axis, you've rotated your state by an angle of 2 theta. Okay? And every time you do this operation, you get an exponent. So it tells us that if we want to kind of measure, we want to bring our state all the way to the y-axis, we just need to do this many times. And once we do that, and the two states are very close to one another, we can effectively measure the state of our computer, and just get the state for our item. So this is in principle a way of solving the search, because I started with this initial state that doesn't have information about K star. I apply a set of operations that only correspond to checking my database. And suddenly I got with high probability the output, the location of my item. We can analyze the runtime of this algorithm by understanding that the amount of rotations is performed is inversely proportional to this angle theta. Small angle, I need to do many detections. And actually, this angle, because this overlap, it actually goes as 1 over square root n. So the amount of times this k parameter that I need to run to get the solution actually goes to square root n. And this is fundamentally faster than the linear case, the classical case. So this tells us exactly how quantum mechanics provides us a quadratic speed up when we do search. Okay. So hopefully that was a review, but kind of gave you a new perspective on how to understand the proper algorithm for search. The question is going to be, how do we take this very simple algorithm and translate it into something that is related to a sensing task? Okay. And so we want to build what I'll call a sensing oracle that basically takes a signal that is not necessarily just this database and actually builds something that looks very much like a proper oracle that we can then use to solve it. Okay. So you should, in some sense, be skeptical. We hear that Grover introduced this algorithm and denied it, and no one has actually used it for something useful. So I want to kind of explain why that's the case, and then hopefully convince you that there are ways that we can kind of overcome those challenges. Okay. So first, let's kind of think exactly what are the requirements that we want for this particular article. Okay. So the idea is that I have my quantum computer, and I have a series of operations that I can perform on it, on my quantum sensor, and between them, such that after I run all of this, if I have some signal at some particular frequency, I'll effectively implement this oracle on my quantum computer. The idea is that if my signal is strong, I'll apply the oracle. If my signal is short, I just apply an identity operator. The signal isn't there because it doesn't mean this is present. Right? At the same time, if my frequency is going to be very different, what I want is that this operation still applies an oracle, but it applies an oracle that highlights a different register of my quantum. What is the state of your this is just, it's going to depend, it's going to evolve. Effectively, it's going to be something that is very similar to this rotated thing that I presented on the previous one. You can see that if I do this, I'm effectively only applying an operation on the quantum computer, and eventually my qubit is kind of like decoupled from it. So I fundamentally need to take a signal that is an analog signal that depends on the details of B, omega, and phi, and transform it into a digital response on my quantum computer. And being more explicit about this, I need to map this continuous frequency range of delta omega into the discrete registers of my quantum computer. And I can do it in a robust way in the following steps. I don't know the strength of my signal. So if my signal, oh, these are the registers. And I don't know the strength of my signal. So if my signal shifts a little bit, I still have to perform the same operation on the phone. That should be robust in that sense. But also I don't know the frequency. So if my signal is within the spin and it shifts a little bit, I should still have this same response. And finally, my problem to detect the agency of an particle, I don't really care about the phase information. So I should also be able to do this regardless of the phase of my signal. That's the robust. And I have to do it in a way that both respects the unitarity, because I want this to be primitive on a quantum algorithm, but also something that has high fidelity. So I can make sure that after I run this many times, I can still perform the program. And so, if nothing else, you should think that the key aspect is that we're effectively building a digital response. We're taking a set of a unitary that depends continuously on many parameters, and we're trying to map it onto a discrete unitary that responds. For the experimentalists, we're trying to build an analog to digital converter quantum computers. Okay. So we have multiple strengths, and I kind of want to, for the next 10 to 15 minutes, I want to kind of give you a feeling of the strategies and how we can use them to build a robust response on our sensing operation. Okay. And please, again, stop me at any time if you have questions or comments or concerns. Okay. So I kind of listed them here, but I like thinking them kind of in a sense, we're going to build a quantum sensing protocol like an onion. It's going to be in multiple layers, and we're going to start from the core one, on which we use a form of phase agnostic sensing and adiabatic dynamics to effectively take our evolution and remove the phase information boundary. Okay? Yeah.
It's to your transector of having expense.
Yeah. So you should think that this white, this yellow dot is the end spin. So in principle, it could just be one spin, but it could also be n spins, and that gives you the Heisenberg improvement. What I'm discussing now is how we can also get a computational improvement on top of that. And so you should think that you have n spins over here, and that you're able to interact them with the quantum computer.
Okay, and what the, how are you like, frequency winning these, like,
I'll explain that a little bit better later. It turns out it has to do a little bit with the way that we do this phase agnostic sensing, but hopefully it becomes a little bit clearer. That's a good question. Any other questions? So as I was saying, the core, we're going to try to remove as much information as possible, as early as possible. And the space information goes from 0 to 2 pi, and it's a big window, so we want to discard that early. So at the core of our sensing article is going to be this operation that takes this unitary that depends continuously on these parameters, actually drops away any mention of the phase life of our signal. Okay. So this is going to give us a response alpha that still depends continuously on these parameters. So the next layer of our protocol is going to be something that replicates something that by doing multiple actions of this particular operation is able to take the response from this kind of quadratic thing into something that looks more akin to a phase. And the goal of this is to fundamentally implement this threshold that we need in terms of the P result and allow that the response of the quantum computer to the signal doesn't depend on the detail of this triangle. And this, you can think, I'll kind of explain how to do it, one frequency at a time. So then we need to do it for all frequencies in parallel. So to each, you see, I kind of have this omega p here. We effectively want to associate that the frequency that we target with these operations will be connected to the state of our quantum computer. And this is going to allow us to do this not only targeting different frequencies, but also doing it in a quantum coherent fashion across the entire bandwidth that we're looking at. And together, this is going to build our sensing particle. And that's going to play the role of this group particle that we then place all of it. Okay. Make sense? Okay. So let me try to give you a feel of these different ingredients, because this is fundamentally the construction of the algorithm. It's building the sensing particle. Because once we get the sensing particle, we just need to do this Grover diffusion, which is just an operation of quantum. Okay, so let me give you a deeper explanation of why this phase elasticity is so important. So what we learned kind of from North is kind of like, in some sense, if I want to measure an oscillating field, what I should try to do is like tune my sensor to be on resonance with this oscillating field. And if I look at the rotating strength, the strength of this field is going to be proportional. It's going to depend, it's going to just be a simple phase that I pick up. But crucially, it's going to be dependent on the phase of my signal. If I don't put my qubit on lockstep with the signal that I'm trying to sense, effectively, I won't get any phase. So what this tells us is that this sensing approach, while being very simple and very nice, it actually is very dependent on phi. And so if your phi is 0, you pick up some phase. If your actually signal is anti-related, it's not in phase with the basic that you chose, you actually pick up phase on the other way. And sometimes you don't even pick any phase. And so in some sense, we want to move away from the linear sensing so that we can kind of like hide the phase information as much as possible.
Can I take this as what you mean by homodiag sensing? The phase has to be along the right quadrature, or it's
Probably. Think of homodiag in terms of photons, but I think that's the basis. I think it's an idea which is like the way that you build your homodiag, like two sets of phase that you're sensitive to. If you set the phase wrong, you don't sense the state. Okay. And this fundamentally sets a problem, because if we do a sensing operation in this fashion, depending on the phase of the signal, you're going to get a different behavior. And because you don't know the frequency of your signal, you cannot always lock to the phase that you care about. If you knew the phase but didn't know the frequency, you're still kind of screwed. Because every time you do the sensing operations, you effectively sample a different phase. And so you'll be doing different sensing operations. And actually this adds decoherence and actually makes your evolution dependent on the phase in a way that we don't know how to effectively implement. So the key insight is that we want to start from scratch and actually try to build a fundamental building block that doesn't have these concerns. So we need this phase elasticity to be more robust. And the idea is that instead of thinking the signal being in the x and the z direction, proportional to the quantization x of our qubit, we actually want to think of our signal in the other direction, slightly detuned from our qubit frequency. And the key idea is that if you think of it this way, the action of this field, the presence of this field, effectively induces an AC star to on signal on our qubit. And that allows us to effectively accumulate some phase that depends on the presence. So that allows us, if there is a signal with some strength, your qubit is going to be sensitive to it and pick up an additional phase. And by thinking correctly, firstly, you can think of arbitrarily large phase. Make sure that you build a large sensing operation. You might worry, but Francisco, now I'm no longer linearly sensitive to my signal. It turns out that if you choose between the order of the signal strength that you care about, you can basically eat up constant factor. Doesn't change the scale and the state of the okay. And so you can understand this very cleanly, and the phase still plays a role in the dynamics of the sensor. But the idea is that you prepare your sensor pointing, for example, in the one state. Once you're over here, what it basically does is it processes slightly canted axis, and the phase accumulation is effectively the size of the circle and how many times you go. Now, to do this in a robust way, you actually need to be lucky because you need to make sure that you come back exactly to the right initial point. Otherwise, you pick up an error in the principal scales with kind of this ratio between the B field and delta. And this is not good because I told you that I'm going to set this to be a constant. So then I pick up a constant error and that's going to mess up my quantum model. So the key idea is instead of just coupling our qubit sensor to the external field, we actually control how much we couple it. We kind of use an adiabatic thread of turning our qubit, our qubit to interact with the signal and then back. And if you think about it, now instead of just very brutally processing around this axis, you're effectively allowing the qubit to go out and come back. And if you pick up a dynamical phase that still depends on the pendulum. It turns out that if you choose this to be very, very smooth, as probably all the experimentalists in this are kind of not, yes, you shouldn't just turn on things, you should like do it smoothly. You can actually guarantee that the state goes out and comes back in will exponentially bulk on kind of like the process. And this allows us to effectively pick up a large amount of phase, even though you allow us to pick up a significant amount of phase while guaranteeing that the error of this operation is quite weak. And crucially, the angle phi matters into what direction you go out and then hit on this block sphere, but it doesn't actually affect too much of this exponential amount. It doesn't affect exactly the amount of phase that you can become and other things. And so this fundamentally allows us to take this unitary and basically transform it into a zero rotation, conditional on the strength and the detuning of our signal. And this is going to be this is the detuning with respect to this omega k that I put in my hand.
The tuning is very simple.
Yes. So here, I'm sorry, I'm kind of using h bar equals 1, so I'm kind of playing where the coupling strength and kind of like the frequency of the qubit are all in the same units. But yeah, does that make sense? There's always like some coupling parameters. I'm kind of like putting all the coupling parameters into what I define as B. So that includes the susceptibility of your system to the particular signal that you're trying to.
Wouldn't that during more sensitive?
Yes, so that's why you need the detuning to be on the order of B. That comes from like the analysis of these like smooth perturbations. It's kind of like you're effectively doing an adiabatic graph. But you don't get like an exponential improvement, you get this factor. Yeah. So this turns out that you can do this on a time that is still proportional to B. Because what gives you this, you can think that what gives you this error is not necessarily the strength of this field, is the fact that you decide to kick it very abruptly. So by smoothly going out and in, it's the same amount of sensing, basically the integrated area of this curve, but in a way that allows you to go adiabatically go in and out. So yeah. The fundamental thing is you can always design a function where the area of this is of order 1. And so that allows you to kind of like do the same amount of sensing. Of course, that I think your intuition is correct. That if I just have it on my field, I would be sensitive also on these areas. So I do still eat up the constant factor. But scaling wise, this is why I kind of focus. Scaling wise, you're still not looking worse. That hopefully that kind of sharpens the point of them. Okay. Awesome. So I told you how to get rid of this phi, and now I want to build how exactly we rectify the signal and take this rotation that depends on the details of the detuning and the strength of the field, and try to get something that looks more like a digital response. Okay. This is kind of like uses this idea of quantum signal processing, and then allows to take this operation, this Z alpha, and apply multiple times, and you kind of get an approximation of what effectively whatever function we want. And I want to kind of make this a little bit more precise and give you a little bit of an example. So for reasons that are kind of, it turns out that this is easier to think if we kind of flip the basis. So imagine that our signal is actually the x basis, and we have some control operation that we can perform, which is on the z rotation. So fundamentally, the key ingredients for what I'll discuss is that we have a rotation that we only have access to. This is our z of alpha in this slide, is the x of alpha in this slide, but the z of alpha in the previous slides. And then I have an additional level of control, which are rotations across a perpendicular direction. Okay? And the idea is that I want to understand how I can manipulate the response of my system by intercalating rotations with respect to what I have access to, with orthogonal rotations with respect to this other. Okay? Make sense? You can basically give an example of like why this gives you additional control by just understanding, for example, the matrix multiplication when I put control in there. There's a little bit of algebra. I tried to put the algebra here to give you a feeling. It turns out an easier way of phrasing this, instead of having cosines and sines, is to think of cosine as an a parameter and sine as the square root of 1 minus a squared. And what you can see is that your initial rotation had a parameter here that was linear in a. And so if I take two of them and I sandwich them between this particular by 5, what I can actually work out, if you work through the math, multiply this way, you pick up a bunch of 5s. And if you multiply the next one, you find that what you see is that you picked up a polynomial over here that's no longer linear in A, but it's actually quadratic in A. And the coefficients that you pick up depend on the choice of the 5s that you make. Okay? I'm going slowly here, because the point that I want to emphasize here is that this, by having these additional control, effectively manipulate the response of my qubit and go from a linear response in this cosine alpha into a nonlinear response. And the nonlinear in this case is like a polynomial of degree 2, because I applied 2 x operations. Okay? It turns out that this generates. If I now put a z of phi 2 and another x of alpha, I can generate a polynomial here of degree 3. And you see that the parity is always, in this case, I only have the even terms, in the other case, I would have only the odd terms. So what this, one way of understanding this QSP is that it allows us to take a response that is in some parameter, which I call A, and build polynomial responses on that parameter. And actually, at the end of the day, my response is going to take this form. Polynomial on the top left corner, same polynomial on the bottom right, and I'll have another polynomial on the other. But crucially, this P of A, this P of cosine A is going to be a polynomial of the degree of the number of operations that I perform. Okay? And so if I want to have a particular response of my qubit, what this tells me is I can actually try to just build it by trying to find a polynomial approximation to whatever I can. So what I want in this particular response is effectively a step function. So you can use these tools to basically build by many of these z's, or this x for the z's in the original frame. You can find multiple of those, and by choosing these parameters phi and the probability, this is something that you can do before you start your experiment. You can basically get a response that gets as close to that gets very close to the step that you have. I won't go into details, but you can do, because of this now we can do semantics, but given a range where I want this to be true, how well can I build a polynomial approximation to a step function? And it turns out that the error that you get is actually small in the number of operations. So it turns out that the coefficients are not always super nice, but from the scaling perspective, tells me that you can effectively build kind of a rectification by doing a few of these testing operations. Okay. I feel like that was kind of like a lot that I encoded, so kind of like give the room some time to breathe. Since then, ask any question.
rectifications.
So in this case, I kind of jumped the logic by saying that you can choose this. The point is like, you can build a polynomial P. And you can build a polynomial of degree L by using this approach, using L instances of this object, right? So now I just want a polynomial that if my alpha or my strength of my field is small, this is 1. And if it's large enough, it becomes -1. And so by building that polynomial, or maybe that's a little. So you want that function of D. There's effects on D min. And the idea is that there's going to be a regime where I don't care about the response to my signal. But if my signal is small, I want that the response is effectively this. So I want P to be approximately 1. And then if I over here, on this regime, I want that my response effectively implements a pipe rotation. So I want my response to be this. Okay. So the function of this B, I want something that effectively looks like a step function for my P. And so I just need to build a polynomial approximation that maps between these two regimes. And that's where you need to now spot that allow you to get this. But crucially, if this is kind of like, if you have a big enough chasm that you don't care, and you can build this, you can do this exponentially well in the degree of your polynomial. That kind of makes it a little bit clearer.
Let's look at the truncated sequence. These cosines.
I think maybe there's a way of thinking about it that way. I would think of kind of like, this is kind of signaling processing. This is why this is called signal processing, because you take something that is linear and you now able to build arbitrary functions. And this kind of tells you like the shape of those functions. That makes sense? Awesome. So what this tells us is that we now took the next step. We initially eliminated this pi information. We now took something that in principle dependent on this details of the tuning and the strength of the field, and now we actually rectify the signal. So if the signal is larger than something min, it's kind of like close enough what I'll call a frequency. I'll explain this a little bit more. You get a pi rotation impose -1 side to the dynamic. If not, your evolution is true. Okay. So now let's go back to understand what we mean by this frequencies in this omega bin, what exactly we do by doing this capital bin. Okay. So indeed, we kind of like, this is just me copying the previous thing. So the way that you should understand this is what I told you so far is that I can pick up a reference frequency, let's say omega 1. And fundamentally, I am sensitive to some detuning. I'm not sensitive to that particular frequency, but I'm sensing a little bit away the difference that's about B min. And I'm sensitive to signals that have height to B min and whose frequency range is also of the order B min. This is what I define with my frequency spectrum. If I have a signal within this blue region, then if I prepare my sequence and use this reference frequency for one, I'll be able to get this rotation. Otherwise, I'm getting a trivializing. Okay. And so the entire construction line 4 allowed me to build a robust detector for one single band. And I'll do the most serious thing possible, which is just say, if we do this, now you can just do it in superposition. So the idea is that for each register of your quantum computer, you associate one of these little errors. Okay? And if you take our previous construction and elevate it such that the frequency, the reference frequency of your qubit now depends on the state of your quantum computer, you're now not just measuring one particular frequency, you're actually measuring across the entire set of frequencies, depending on the state of your quantum. And that allows us to kind of do this in a quantum coherent way across the entire no problem. Okay? And this fundamentally tells us that if your quantum computer is in state K, and you have a sensing qubit, final evolution is going to pick up a minus sign, which is the one that I plotted here, if there's a signal in that particular bin, but otherwise the evolution is going to and change. Okay? And this is exactly the structure of the Grover particle that we wanted to make. Okay. Also going to give you 30 seconds here, see if there's let us sink in. See if there are. Yeah.
What is the bandwidth, interpretation of the bandwidth that you can sense this is related by the dipole?
You mean the whole thing or the size of these?
The whole thing.
The whole thing is a parameter that I want to do. If I have a bigger range, now I need more bins. I need a higher nonlinearity between my quantum computer and my sensor. Awesome. Okay. So I kind of told you all the ingredients that go into building the sensing particle. So this felt kind of like a little bit complicated, but it turns out that if you draw the circuit diagram, that's quite simple. So the key idea is that you have a quantum sensor that you're doing some form of evolution, and you have your quantum computer below. The way that this algorithm goes is that you prepare your quantum computer in the equal supervision in a coherent state that we discussed before. So we have a quantum sensor in this particular state, and then you need to do this QS. And that involves doing some rotation around X. And do this sensing operation that involves the quantum computer and the sensor. And this is kind of like the sensing that way. Now, by doing effectively L rounds of this object, you effectively implement this quantum sensing signal processing. And because you did this in a correlated way between the quantum computer and the sensor, this implements the sensing particle that we defined. And to implement the entire Grover algorithm, you now just need to do this Grover diffusion on the quantum computer and iterate that for a time and is the number of frequency bits when you're searching on it. You can actually look at this, measure exactly the runtime of our algorithm. You can see that if this there's kind of like a sensing time T here that kind of going to set the total sensing time of your system, and that you can actually show 1/d min, where n is very much the Heisenberg improvement that you get of having not just one quantum sensor, but actually having n in an integral state. And then you think of the number of frequency bands that you need, that has to scale with the size that you're sensing over. And for each size, basically, the smaller the signal, the more bits you need to do, because each signal is bigger. Each bit, the frequency width is smaller. And as I alluded, this L, you can do it very efficiently, and it turns out that it's only logarithmic on square root n. So the total sensing time, the total duration of your protocol as measured by how long you need to sense is actually just the product of these things that takes up this form. Okay. And now what I want to kind of that there's a model that we made the Grover Heisenberg limit that says that any problem that solves this test has to take a time greater than this without this polygon. So I'm saying how much am I doing time? Okay. So, okay. Let me, I think, okay. I told you how to build the algorithm. 10 minutes. I want to tell you a little bit about these results and how you can implement it. Yeah.
You, I guess, assessment of partial relative or like in the preparation of a state like searching for a lot, not all the time, but sometimes you can find some knowledge of the
mean, that's create that structure.
So if you had knowledge of that, in principle, you knew that the signal was there, so you could solve the problem. So we're kind of like assuming that there's no prior.
Not the entire ultimately necessarily, so like if you know like some kind of range where it could be, where the range is like a random distribution, not random distribution, but instead of spanning the entire aggregates, one computer, it's subsections where you can check those subsections.
That's gonna control like the size of your bandwidth. Because everything, like instead of being from 1 megahertz to 100, it's actually either between 1 and 5 and 95 and 100. And then that just says like how big we right? Because our signal is not a Hamiltonian or it's literally a classical oscillating field. So it's only determined by this parameter omega and beta. And those enter in the direction of our protocol in this protocol. You seem to give me some confused looks, but maybe this is something that we can discuss at question.
What if there's no signal? Is this still kind of get this implementation?
So if there's no signal, effectively what you always will net, so you don't do anything like over here. You do go back and forth like before. And it turns out that you can just get a random string. So it turns out that to finalize this, that's you have a sharp eye, because you actually need to add a verification step. But that verification step only scales with this vector, so it can be absorbed into this. But fundamentally, at the end of all of this, you always need to do a verification to make sure if there was a signal or you just got the random bit. Very good question. So I think I planned some slides with a little bit more detail than I'll have to, but I'll to comment on. But I kind of want to give you a little bit of flavor of what we call this the Grover-Heidelberg. So how we prove that there has to be some finite time on which we run this about. Any algorithm that solves this has to have a particular scaling. And the idea is that no matter how you try to solve this problem, you need to be able to distinguish whether or not there is a signal. Okay? And so every time you try to do a sensing operation, there's kind of this concept of distinguishability, which is the method of the overlap between the states, that can only increase quadratically in the number of sensing operations that you do. And there's a parameter that's I'll call it squared, that measures how much additional distinguishability you get for each sensing step. Turns out that this is fundamentally how people prove also optimal. You can't do faster than squared because of similar concern. The difference between our protocol and Grover's proof is that in Grover's proof of optimality, the delta is exactly 1. But in our case, it has to depend on the parameters that we're using. In particular, you can show that this delta squared for the sensing operations is to go as b squared times the duration of this set of each step divided by the problem. There's some equation to this. If your frequency range is very large, you won't be able to measure a lot of the signals, so this distinguishability at each step is going to be small. If your signal strength is large, you rotate a lot to be able to distinguish the states more effectively. Usually this works for small time, but we can kind of like use these kind of ideas to build the sequence of many steps. And this fundamentally, if you force this distinguishability, that has to be lower. This factor. If you force this to be a order 1, that's scaling on how fast your algorithm can run. This is just from the ability of like distinguishing these states. These are all in terms of B. You can put back the Heisenberg factors by changing B. You get exactly this scaling. Okay. Turns out that you can now ask the question, how long this compare to classical or conventional quantum sensing? And you can show that it's hard to exactly make a distinction between a quantum computer and a very complicated quantum sensor. But actually, under different notions of sensing, you can actually show that there's always a separation. I'll not go into details, but in general, in different settings, whether it is particular like a CPMG kind of sensing, or whether you use QFI try to like maximize the QFI over the entire broadband regime, you always find solutions that don't scale as well. There has to be this interplay between the quantum computer and the quantum sensor in a way that's distinct from the previous approach. Maybe not too much on this. So this kind of tells us that this approach fundamentally does differently and does better than what a conventional quantum sensing approach does. And that's kind of like, it kind of opens up a new way of thinking of different kinds of quantum sensing tests. And so, finally, comment exactly how hard it should in principle be to explore this. And again, if you look at the circuit that I presented before, there's actually not that many elements. Right? There's this rotation of the qubit, of the sensing qubit, which in principle just like some control operation on the qubit. There's this sensing operation that depends on an interaction between the quantum computer and the quantum sensors. And then there's an operation on the quantum computer, but actually the only entangling gate is this like many bodies indicate. And it turns out that if you think of the requirements for this interaction, what you want is that the frequency of your sensor depends on the set of the quantum computer. One way to achieve that is to basically add Ising interactions, such that the qubits that define your computer have your sensor, and depending on the state of your quantum computer, you can get different the bare frequency of your qubit of your sensing qubit changes. It turns out that if you have those elements, you can actually also use the sensor as a way of implementing the Grover diffusion and implement this. So at the end of the day, if you have sensor qubit Ising interactions that you can control, or maybe they're random enough, individual qubit control of the quantum computer and the quantum sensor, you fundamentally can implement these kinds of algorithms. If you want to do this with an Eisenberg improvement, where you have also, instead of preparing that in a plus state, you actually prepare a TNC state, you need to be a little bit more mindful, because now these Ising interactions don't interact so well. And there's kind of a little bit of caveats there. But if you think of this as kind of like a single sensor coupled to a quantum computer and using that for a new form of enhanced, you actually have a wide range of platforms where you can get standard physics, because you only need some sort of control and dispersive coupling between the different elements. And we kind of like took a hold and tried to estimate exactly what would be the requirement in thinking in the context of solid state spin platform. So the center, this is going to be the quickest introduction to the anti-center. So the anti-center is effectively an electronic spin defect that lives in the diamond. You can think of basically the two sides of your carbon lattice. One disappears, the other is substituted by nitrogen. And the ground state of that defect is actually spin 1 degree of freedom. And if you apply it a magnetic field, you can isolate two levels and follow the unit. It turns out that if you have single NV, it's going to be surrounded by other defects. Often, your sample is pure enough that it can be just nuclear spins. And if you have these nuclear spins, they actually interact very weakly with each other and with the outside world. So that kind of gives you a platform where you have something that is more reactive to the outside world, this electron spin, coupled by an Ising interaction to a bunch of other nuclear spins that are much more weakly coupled that can act as your quantum register or your quantum computer. And it turns out if your field is large enough, it actually has a shape of the Hamiltonian that we carry. We have kind of like a carrier frequency set by the base frequency of our NV, and then you have these kind of quantum register dependent shifts that the NV feels depending on the state of these nuclear spins about. And so if you look at the spectrum, depending on the state of your nuclear spins, you're effectively NV frequencies, and that is exactly how you should think of these omega I in our proposal. Now, this is not the equally spaced omega that I kind of assume for our protocol, but this kind of tells us that there are platforms where you can have this kind of like strong interaction between the elements. And if you have this kind of platform, you can actually perform a CZ gate very easily. So the idea is the CZ gate is basically you pick up a phase of -1 if your quantum computer is in the all-up state. So what you can do is effectively, if you drive your system weakly at the frequency associated with that particular state, you can actually go up and down and implement two-pi rotation, much analogous to when the Stickler Levin-Pickler gate that Misha told us about. And by doing that, you can kind of like place a -1 sign exactly on one of the registers. Computer implement this easy. Okay. So what I'm going to tell you next is that if you now think like not necessarily the full algorithm that has all the robustness, but a proof of principle that in principle gets the quantum computing enhancements out, you can actually also do it in this platform. And the idea is that if instead of assuming that we're searching over a large broadband with an unknown string, if we kind of restrict our problem to looking at the discrete set of frequencies that are just going to be the frequencies of this dispersive couple, and I have no strength of my magnetic field, can now also implement the article in a very similar way, where if there is a signal somewhere and it lines up with the frequency of one of these induced by one of these registers, you can time the way that my system interacts with the signal such that the signal itself also implements a two-pi rotation and implements the analogous of a CZ gate, but for that particular register. And this is nothing more than a Grover article that we wanted to implement. So I want to emphasize that this kind of approach is a much reduced setting that doesn't have the robustness that I told you about. So one has to think a little bit about in what sense you can get an improvement. But what we saw is that, let me just kind of specialize. If we put all of these elements together, and we think of the sensing oracle in the reflection, we have that we need to measure the sensor, the signal for some time, and then we need to do this program reflection that corresponds to an applied signal that you perform. Okay. And what we found is that if you compare this kind of approach using kind of like optimistic but also realistic parameters, you actually can have an improvement, a faster way of detecting the presence of a signal in one of these frequency bits. So what I'm plotting here is effectively how much faster you can solve the problem if you use this quantum computing approach versus how you do this classically, on which for each frequency you effectively try to see if the signal is there by doing effectively pi mediated by a signal. And what you see is that in this approach, having register of a few number of qubits, in this case 8, you already see an improvement of factor between 2 and 4 for kind of like coherence times that are on the order of like there are kind of like reporting gates. Okay. And you increase the number of qubits and you increase the coherence time of your system, you start seeing this exponential improvement that arises from the fact that you're probably an exponentially larger number of frequencies. Okay. So it helps that these ingredients kind of lead us to ways of using these ideas in near-term experiments. Hopefully I can do some experiments later and see if we can do it. But with that in mind, I kind of want to conclude here. I kind of told you of what's called build protocol. I think quantum sensor coupled quantum computers can reach a new kind of improvement in sensing. And I think like this kind of highlights if you think of sensing more broadly and not just in terms of like parameter estimation, there's a lot of opportunities that we can cook up and try to think of like better ways and faster ways of using this resource for sensing. And this is something that not only is kind of like a nearest dream, but it actually is trying to solve a problem that people want to solve, and it's something that doesn't require the amounts of resources. I think that this is something that bridges in a meaningful way some of the advantages that you can have from quantum computation. Even in the case where you have a noisy quantum computer that might have some finite coherence time as well as your system. Okay. And if nothing else, and I think like why I think that this is like a thing that is meaningful to talk in the school, is that I think that this kind of opens up a new set of because what we've effectively built is a way of analog signal and digitizing it into a quantum computer. So from a broad perspective, what we're now able to do is try to think of algorithms, think of applications where we can connect a quantum computer that we think in terms of discrete gates and discrete operations, much like Christian should kind of emphasize, try to interface it with the role and try to get it kind of like new approaches based on that kind of like integration. And with that, let me thank you for your time. I think I've already quite a
Other questions, perhaps, time, but
I wonder about the ability to do parameterization. Can you, or at least know the moment of the game? Because of the minus over it. Yeah, so and then. Instead of spectral binding, we can phase binding, or magnetic field binding. That running over different frequency windows, running over phase window, and find the correct phase, go ahead and anything target. Yeah. So the way that you should understand this problem is kind of like zooming in. So what this tells you is if there is a signal, and it actually, as you said, it actually tells us which bit the signal is in. So imagine that you're searching over 10 hertz or like even more of the frequency space. This tells you within megahertz where the signal is. And then you use all the tools of parameter estimation to nail that down. So you should think of this as kind of the initial element on which you then do parameter estimation to get as close to the second about the phase information, the strength information. The issue and why one way to understand why we can do better is like to do parameter estimation very efficiently, you need to have an understanding where the signal is. You effectively look at the signal, you have an estimator for it. And then you try to kind of like linearize around it and get a better estimate. If you're searching over a massive bandwidth of a very small signal, you don't know where to start. This protocol tells you where to start, and then you can move all the way to nail down the curve.
Yeah, I understand one side, you nail the gym added on. So, yeah.
So in principle, you can this is defining meaning with other. But in some sense, like for example, B, it doesn't make sense to bin in B. Because if your B is big, you can more easily detect the signal. So what this tells you is like you should always do this to tell you the overall strength of your signal. But it doesn't make sense to try to search for smaller signals, for example. You could try to do a binning shortening in place. So that might work. We haven't thought of it yet. It's already still
You have a modulation on the signal.
what do you mean by modulation?
Well, now it's a single tone, if you have a modulation, you don't know modulation.
That could be, and that could be a generalization in which now you're not get a cosine signal, but could you develop algorithm where if you have two tones, you can make a better statement of like the devil. But one thing that I want to kind of emphasize, and I think just to make sure I got this point home, is that this is not necessarily a way to get parameter estimation. This is kind of a fundamentally different problem, and that's why we get a different form of advantage. Because we know for parameter estimation, you can't do better than a Heisenberg. So what I want to kind of convince you is that we should think of like some of these questions sensing a little bit more broadly. And by thinking of them a little bit more broadly, we might have ways of doing it faster. Yeah. Does that make sense? Yeah.
So this is more issue about. It's not almost and the origin, this is a.
So there's different kinds of like jitter of our signal. So let me kind of address the different one. So the simplest one is, let me see right. Yeah. So maybe, okay. So the simplest one is, as you said, my neutral changeable. For a function that we build in terms of B, guarantee should tell me that that should affect. Kind of go all the effort to kind of ensure that if we change the B strength a little bit, it doesn't affect it. The other ones that might be, and the same for the frequency. If we change the frequency a little bit, you should still be robust. The thing we don't know is what happens if the phase coherence of your signal changes during the dynamics. So that's something that we haven't analyzed. We expect that that fundamentally works as kind of an effective T2 that might come in and set some error on their linear particle, but we don't get.
So the. Knowledge. Strength is wrong, just like. Right. on the threshold.
Yeah. Yeah, so in principle, we can set this so that the min is a little bit further away, and then it becomes like how far we go. It will might mess up things because we don't have control of what happens if the signal is over here. If basically we get a random out, and we don't care about a random answer because at the end we verify. So in principle, in good method for algorithms, we're not doing Grover, but we're doing something else. In principle, that's just going to give us a random outcome, and then when we go to verify that random outcome, we won't see the signal, and then we'll say, again, the signal is below this threshold, so we kind of still solve our problem. Is that
Protocols to apply to time that versus precise time. There is more time. Give the frequency. But apply for the timing and try to experiment low time dynamics.
so? What do you mean by that? You want to?
Like, I mean the signal that the change in the signal I'm detecting at for small time scales. Can use quantum computers.
I think we need to make that question a little bit more precise. The reason why it's kind of the sensing thing is that you need to there's kind of a fundamental limit to how many traits you can accumulate by having your signal interface with the signal, your sensor interface with the signal, and that sets a limitation. If you're assuming that you're able to measure the properties of your system for fairly short times, that's a very different set of questions. It's more like on the question of like Hamiltonian learning and some of these things. So there might be all opportunities there. I just don't. I think we need to sharpen that signal a little bit. It's the limit of B. What's the limit? B-min is just a parameter. So depending on the strength of B-min that you have, your protocol takes longer.
Physical, I guess at some point, there's that one limitation.
Yeah, so this is kind of like if you're a draw keyboard, there's many limitations. For example, at very high frequency, you can't control your quantum computer fast enough. And now there's kind of like always going to be a cutoff, which is how fast you can manipulate a quantum computer. There's also another limit, which is this improvement that we saw. You can think of this as the number of bits. The number of bits is due to the number of qubits on your quantum computer. If you have quantum registers with only a finite number of qubits, there's actually an upper bound in how much you can do this, and that's going to set another limit. The limit of B-min, the smallest you get, is actually set by the coherence time of your system. You can understand that if you're starting at a super weak signal, but you have some decoherence, you're going to take you can't measure the signal before your decoherence hits, and that kind of comes into play. And actually, we can kind of this is kind of like emphasize on this point, which is like this analysis is what happens if you do have some coherence time. And what you see is that if T2 is infinity, you actually should recover this, so it doesn't just go to zero. But crucially, if T2 is finite, this is just a classical approach times the improvement that you get of solving smaller problems in that T2 time. So they're kind of like in the interplay between these topics. Hopefully that kind of like just like gives a little bit of intuition. Yeah, so the resolution and frequency depends on the strength of the signal that you're trying to measure. So resolution, the width of each frequency band is on the order of the signal strength that you put that. So
Even convert 50 million for
yeah, no, let me try to understand exactly what you mean by apex, and so make sure we're making this.
I mean, just number of bits and if conversion. You go 16, like into a classical, that's high. Keep this. Actually, very much looks like it's
It's maybe, analog, so what needs to be careful of like, when you're saying analog and convert, I think I have a signal. And then it kind of discretize it into the bit number. But here, here we're not doing that. So at the end, I don't get like a digitized version of the signal path. But what I do get is a digital response of my phone. That's what I mean by analog to digital. And the bit information that I get effectively ends up being the number of frequency bits. So not only I tell you exactly what's the shape of the protocol of the signal digitized in this way, I just tell you the presence amount of the signal within a particular number of bits. And those are given by effectively the log increase.
So I would suggest, Francisco is not running away. I asked the gate to be locked. So I think it's the perfect subject to sort of huddle around for at lunch with Francisco and discuss this. So
Thank you so much.
fair enough. Thank you very much. Gene?
No, that makes sense.